So we've been finding an upper bound for the error in estimating S using a finite number of terms of S. There's also a lower bound for the error, which turns out to be quite useful. So let me show you. We can basically just pop back to what we drew back here and say, all right, what if we just take this picture, and instead of doing left-hand sum, we'll do a right-hand sum. So we're just going to shift everything over by 1 unit. And then we're going to have a sub n plus 1 over here and a sub n over here. So here's a sub n plus 1. Here's a sub n plus 2, and so on forever, right? A sub n plus 3. So what we're going to get here is that this a sub n plus 1, a sub n plus 2, plus a plus n plus 3, all right, is also larger than something. So we have here that it's smaller than something, but it's also larger than what? So this sum, the error, the remainder, r sub n, is larger than if instead of doing the integral from n, I did the integral from n plus 1. So if I do the integral from n plus 1, I'm going to have this area right here, but the remainder sum is outside, consistently outside of that function that I'm using to estimate, that integral that I'm using to bound the error, that area. Yeah, I was going to say something about that. Oh yes, that all of this, you know, the fact that the right-hand sum underestimates the integral, and therefore the integral is greater than the right-hand sum, and the left-hand sum overestimates the integral, so the remainder is greater than the integral from n plus 1, depends on the fact that this is a decreasing function. And if I didn't have a decreasing function, boy, none of this would be any good to me at all. However, if you don't have a decreasing function, then the sum's not going to converge. I mean, well, there are sums that converge so that, you know, they would be modeled by a function that sort of goes up and down and up and down and up and down. So the limit of the sums always has to be 0 no matter what. But if the function is not consistently decreasing, then all of this analysis goes out the window. All right, so this we can't have. But, you know, we've looked at a lot of different functions, and they tend to just nicely decrease towards 0. That's what a lot of sums do. So it's worth doing all this analysis. Anyway, what we've concluded is that the remainder, an plus 1 plus an plus 2 plus an plus 3, etc., is greater than the integral from n plus 1 to infinity of f of x dx. All right, so the full statement of this remainder theorem is, if I can find out what page I'm on, the remainder r sub n, meaning the error incurred by using finitely many terms, n terms, to estimate the infinite sum, is less than the integral from n to infinity of f of x dx, where f of x is a function that models the sequence, so f of n equals a sub n for all natural numbers n, and as the r sub n is also greater than the integral from n plus 1 to infinity of that same f of x dx, which I squinched in there. All right, and that is the full statement that you have on page 680 of Stewart-Krakowka. There's page 680, and there's the full statement of the integral test. All right, again, I often encourage you, read this whole section. So you've got the advantage of one of the most readable textbooks I've ever seen. Being able to read textbooks is a great skill to have. All right, well, so what? How does that help me? How does it help me to know what the least my error could be is? Well, if I know that I've made an estimate and I know that my estimate is at least this far off, why don't I take this error and just add it on to what I had, and then I will have a better estimate. So that is, in fact, what we do with it. So here's what we're going to do next. For this sum, n equals 1 to infinity of 1 over n cubed, the same sum, but I'm going to do a different partial sum. We're going to find the 25th partial sum, s sub 25. We're going to find an upper bound for the error. We're going to find a lower bound to the error. We're going to use that lower bound to the error to improve the estimate, and we're going to write an inequality bounding the value of s. And if you think you're pretty good with this stuff, you might try this on your own. But if not, just hang in there, and it might take me 2 videos to do it, but we'll do it. All right, so first of all, what is the 25th partial sum? Well, let's see. I've got it in here, and I can just copy here and change my 23 that I was using for the last problem and just make it a 25. And I've got 1.201288. All right, so so that's all I have to say for that. S sub 25 equals 1.201288. I really should say approximately equal to because I've rounded it off, but it's pretty easy to get excessively neurotic about using the approximately equal to, a problem which I'm probably guilty of on numerous occasions. All right, now we're going to find an upper bound for the error. So this is what we should be pretty good at by now. So we're going to say that r sub 25 is less than the integral from 25 to infinity of 1 over x cubed dx. And so, we kind of have a pretty good idea of how that's going to go. It's going to be the limit as b approaches infinity of, let's see, what did we say? It was negative 1 over 2x squared, right? From 25 to infinity. All right, we know that when we, so that should be a b right there, right? That's a b because we're doing limit as b approaches infinity. We know that we would plug in the b, we're going to get 0. So let's just put that right away. And when we put in the 25 and we subtract the negative, we're going to get 1 over 2 times 25 squared. 25 squared is 625. 625 times 2 is 1250. So it's plus 1 over 1250. All right, so that is our error bound. I did throw this into a calculator to get a decimal, but I forgot what it was. What was it? I think it's 0.008, but I can't remember how many zeros. Yeah, it's 0.0008. That's exact, too. All right, so that's our error bound. That's the part we already know. Now we're going to do part C. We're going to say what r sub 25 is at the least, and it is at the least the integral from n plus 1, which is 26, to infinity of 1 over x cubed dx. Now here's how else we can cheat on that integral. So we already did the integral from 25, so just instead of 25 squared, we're going to have 26 squared. So I did that ahead of time too, but I totally forgot what that was. But anyway, it's going to be equal to 1 over 2 times 26 squared, whatever that's going to be. All right, so 1 over 2 times 26 squared, let's find it here. 1 over 2 times 26 squared is 7.39 times 10 to the negative 4th. All right, so that is 0.000739.6. Now you can see that, like, we've really tightened up. This is this minimum for the error is really close to the maximum for the error. So it's going to create a tighter interval where S can reside. All right, so the maximum S can be, S has to be less than S25 plus 0.0008. And S has to be more than S25 plus 0.000739.6. So all I have to do is figure out what those numbers are, and S is between them. All right, so let's take our S sub 25, and we'll add the 0.007 number. All right, so let's see, where's our S sub 25? It's right here. Oh, so we can just do this plus this. You can see that, okay? Yeah, okay. Enter, enter. And it's 1.202027. All right, 1.2020. It's really 28. I think I'm going to take that rounding right there. All right, I'm using a lot of decimal places because we actually have a good deal of accuracy. All right, that's the least the S can be, and then the most the S can be is going to be the S25 plus the 0.008. So all I have to do is take this number, which was my sum from 1 to 25, all right, and add 0.0008, and I get 1.202088. 1.202088. All right? None of the analysis that you are going to learn in this class, or even in your next 3, 4, maybe 5 math classes, if you even do that many, is going to tell you the exact value of the sum from n equals 1 to infinity of 1 over n cubed. That's a very difficult problem. It might be intractable. It might be unsolvable. I don't know. I don't feel like looking it up. You can look these things up. It's pretty interesting. You'll find a lot of interesting hardcore math. All right, but here's what we do know. Whatever that sum is, it's between these two numbers. And that's pretty tight. See, look, we got 4 decimal places. So we really only had justification ahead of time for having 3 decimal places of accuracy. But by using this improved estimate of adding the minimum error bound to our original estimate, all right, that's our improved estimate. So when it says use the lower error bound to improve the estimate, I sort of didn't really do that. I guess it's here, this answer, which is the 1.202028, all right? That is our improved estimate for C. And then down here, I have part D. Okay. And you'll do things like that for homework. So we managed to significantly improve our estimate, which originally was only 3 decimals. Now it's 4 decimals, just by adding on the minimum error. So essentially what I calculated here is, what is the minimum error? Let's add that on to my original estimate, and then I have a better estimate, which I wrote here for part C, and I'm writing here as my inequality. And then I also know that the most this S can be is the R25 that I calculated plus the maximum error that there could be, and that's here. So S has to be between those two. All right, so that is the idea of finding error estimates using the integral test. There are lots of other things we will learn in the future in terms of finding bounds for errors using various types of estimates. All right, your homework, which will be posted, is the Stewart-Kokoska text, section 9.3, page 683, number 44, 49, 50, 51, 53, and 54. Oh, it's just 6 problems. That's not that much, is it? Well, they are sort of multi-part, and they're kind of hard. Okay, there you go.